Across the vast expanse of the cosmos, there are immense clouds of gas and dust known as nebulae. These nebulae are like cosmic kitchens where the ingredients for stars are mixed and baked. Gravity is the master chef, pulling the gas and dust together. As more and more material clumps together, the cloud's center heats up. This hot, dense core is called a protostar. Protostars are not yet true stars. They haven't started the nuclear fusion that makes stars shine, but they are on their way. The protostar continues to gather material from the surrounding nebula, growing hotter and denser. Eventually, the pressure and temperature at the core becomes so intense that hydrogen atoms begin to fuse, creating helium and releasing an enormous amount of energy. This fusion process marks the birth of a star. The birth of a star is a spectacular event. The newly ignited star blasts out powerful radiation, pushing away the remaining gas and dust. This outburst illuminates the surrounding nebula, creating breathtaking displays of light and color. The Orion Nebula, visible to the naked eye, is a stunning example of a nearby star-forming region. Here, we can witness the birth of stars in action. The mass of a star at its birth is a crucial factor in determining its future evolution. More massive stars have stronger gravitational forces, leading to higher core temperatures and pressures. These stars burn brighter and hotter, but they also have shorter lifespans than their less massive counterparts. It's a cosmic trade-off. Live fast, die young. Once a star achieves nuclear fusion in its core, it enters a long, stable period known as the main sequence. This is the longest stage in a star's life, and it's where our own sun currently resides. During the main sequence, stars are in a state of hydrostatic equilibrium. Hydrostatic equilibrium is a delicate balance between two opposing forces, gravity pulling inwards and radiation pressure pushing outwards. The outward pressure from nuclear fusion in the core perfectly counteracts the inward pull of gravity, preventing the star from collapsing in on itself. This balance is what allows stars to shine steadily for millions or even billions of years. The color of a main sequence star depends on its mass and temperature. Hotter, more massive stars emit bluer light, while cooler, less massive stars emit redder light. Our sun, a yellow dwarf star, falls somewhere in between. It's not the biggest or brightest star in the galaxy, but it's perfect for our solar system. Throughout the main sequence, stars gradually convert hydrogen into helium in their cores. This process releases the energy that makes stars shine. But eventually, the hydrogen fuel in the core begins to run low. When this happens, the star's life takes a dramatic turn. As a star exhausts the hydrogen in its core, the outward pressure from fusion weakens. Gravity, always present, begins to win the battle. The core contracts and heats up, causing the star's outer layers to expand dramatically. The star swells up to hundreds or even thousands of times its original size, becoming a red giant. During the red giant phase, the star's core becomes hot enough to ignite helium fusion. Helium atoms fuse to form carbon and oxygen, releasing even more energy. This helium-burning phase provides a temporary reprieve for the star, but it's only a matter of time before the helium fuel also runs out. For stars like our sun, the red giant phase marks the beginning of the end. As the star expands, it engulfs its inner planets. Mercury and Venus are doomed, and Earth's fate hangs in the balance. The red giant sun will eventually shed its outer layers into space, forming a beautiful but fleeting cosmic cloud called a planetary nebula. After a star like our sun sheds its outer layers, all that remains is a small, dense core called a white dwarf. White dwarfs are incredibly hot, but they're no longer generating energy through fusion. They're like embers left over from a fire, slowly cooling down over billions of years. The planetary nebula surrounding a white dwarf is a stunning sight. The glowing gas and dust, illuminated by the white dwarf's radiation, create intricate patterns and vibrant colors. These nebulae are relatively short-lived, lasting only tens of thousands of years before dispersing into the interstellar medium. While white dwarfs and planetary nebulae mark the end for stars like our sun, more massive stars have far more dramatic fates awaiting them. Their stories involve powerful explosions, the creation of exotic objects, and the ultimate test of gravity.
Like and subscribe to start your journey today.